Welcome to CCNY. Today, I'm going to be talking to you about ordinary differential equations. Specifically, today is the first lecture, so we'll be talking about direction field. So let me see if I can come up with something for y equals x squared. So y prime is 2x. So we can do y prime is equal to 2y divided by x. So now how would we solve this? Well, it's with an old high school technique called separation of variables. So all we have to do is get the dx right next to x and the dy right next to y. Why? Well, so we can integrate. So what I'm going to do is divide both sides by y to get this, multiply both sides by dx to get this. Now, let's integrate. You will recognize that this 2 is a constant, so it can just be taken out. And since we're doing indefinite integrals, we have to add a plus c, which is what gives us a variation in our solutions. So this is just going to be ln y plus c1 is equal to 2 times ln x plus c2. So that gives us ln y plus c1 equals 2 ln x is the same thing as ln x squared plus 2c2. So ln y minus ln x squared is equal to 2c2 minus c1. Now, since these are just numbers, we can make this a new constant. Say c3 is equal to ln y over x squared. So then we get y over x squared is equal to e to the c3. But wait, this is just another constant. Let's say it's k. So then we get y equals kx squared. Anything of the form kx squared, where k is just some real number, is going to be...
How kx squared is energy?
What? No, this is not the spring constant. So anything of the form kx squared, where k is any real number, is a solution to this. Don't believe me? Y equals x squared and not unique. So let's try 6x squared, for example. If we plug this in, we get 12x is equal to 2 times 6x squared over x. Voila. Works just like that. So, what does that mean? Most differential equations have infinite solutions. And that's what you need to come to understand before drawing a direction field. So what is a direction field? You might have been asked to draw it during the final few sections of your AP Calc BC exam. So what does that mean? Well, you have a couple points. It's actually what we call a vector field or a scalar field, in that every single point in the plane has a value attached to it, but we can't exactly draw that. So we take specific sample points and infer the rest from there. So let's try drawing the direction field for y prime equals 2y over x. Now you should be able to deduce that the x and y will be plugging in here are just the x and y coordinates of the Cartesian plane. So 0, 0, we actually have undefined. And that goes for anything on this axis. But for our purposes, we can actually just draw it as a vertical bar. So let's do that. And then I know it may be hard to see against the y-axis. I apologize for that. And when y equals 0, we just have that this is equal to 0. So it follows the x-axis, just like so. So then, what about when we're kind of in those middle regions? So like, for example, 1, 1. How does that work? Well, we just get 2yx, that's just 2. And that's the same when y is equal to x. And we have these special lines, I'm forgetting their name, for when all of these slopes are equal. So for example, y equals x is the special line where the slope of all the points on that line is going to be 2. ended with like a Klein. I can't remember. So, what about 1 comma 2, for example? Is that it? No, that's 2 comma 1. So what about 1 comma 2, for example? Well, that'd just give us 1. What about 2 comma 1, for example? Well, that'd give us 4. And you might be thinking, but how does this make sense if there's a slope at every point in the coordinate plane? It's not like it's not like all the graphs go through every single point, right? And you'd be correct. But all of our variations, all of our infinite solutions for y equals kx squared, both the positive ones and all the negative ones, all of these will end up going through every single point. So, these are just meant to act, these guys are just meant to show if one of our solutions passes through them, what the slope's going to be at that point. And it's pretty acceptable, actually. And you may notice that other than at the origin, none of our solutions intersect. And that's on purpose. With the exception of y equals 0, there is a theorem that we're not going to be proving in this course that none of these differential equation solutions will ever intersect with one another. Now, most of the time, we can only get approximations, and we can't solve for an exact solution with methods like a separation of variables. But the ones we're most interested in are the ones that usually use separation of variables. And so, that's exactly why we're going to be also pursuing the physical application of differential equations in this course. But mostly, we're going to be talking about the mathematical side. So yeah, that's it. I'll see you in the next lecture.